my name is Howard Poston, and I'm going to be talking about some of the common causes of cryptographic vulnerabilities. So, quick overview of what we'll be talking about today. Start out with a why cryptography, because cryptography is something of a specialist subject, but it's also showing up in a lot of applications and going wrong in a lot of applications. So then we'll talk about one of the reasons why, the fact that cryptography is complicated, and discuss where some of the common causes of those cryptographic vulnerabilities are, or where cryptography goes wrong. Then talk about a few case studies before talking about some of the possible solutions to these common cryptographic vulnerabilities and how we can make cryptography in our applications secure. Thank you. And so start out by talking about why cryptography. So the rationale behind including cryptography in application is it hits pretty much that entire CIA triad that we want for cybersecurity. We have confidentiality, keeping things private. We have integrity protections, or ensuring that nobody can mess with the data that we're storing, transmitting, et cetera, without detection. We have authentication. We can prove using digital signatures that a message or a piece of data that claims to be from a particular person actually came from them. And then we have non-repudiation as well. So the ability to prevent people from denying that they took an action. If you've got a valid digital signature on a piece of data, then someone with the appropriate private key for that digital signature is the one that created the data. And so in addition to all of these benefits, cryptography also has certain requirements that make it an essential part of many applications. For example, we need to protect certain types of data, both due to internal and external pressures. Corporate policy probably states somewhere that they want to protect intellectual property, sensitive data of their customers, et cetera. And so we need to keep that encrypted whenever possible, at rest and transit, and if we could, while we're using it as well. And then also, we're increasingly facing regulatory compliance requirements for data protection, data security, things like GDPR, CCPA, et cetera, state that we need to encrypt data. And so, therefore, we need to know how to use cryptography appropriately in our applications. However, often we have trouble with cryptography. And the reason why is that cryptography is really complicated. And these cryptographic algorithms are very finicky. So even a small change in how a cryptographic algorithm works can completely break it and invalidate its protections. And so just because we're able to get code to compile or get code to run doesn't mean that it's secure. So just the fact that, for example, if you have a 256-bit value that you have to pass into a cryptographic algorithm and you create that value somehow, doesn't mean that you're using the right value in the right way. And so with the complexity and finickiness of cryptographic algorithms, we have a lot of cryptographic issues. And the latest version of the OWASP Top 10 made it up to number 2 on the list of the most important or most impactful vulnerabilities in web apps. According to Veracode, it's the 3rd most common application vulnerability, and it appears in nearly 2/3 or 63.7% of applications. So we've got this very vital component of many applications. We need it to keep our data secure, meet regulatory compliance requirements, et cetera, but we're not using it properly. And that causes significant problems. So why are we having these problems? Well, the problem is that cryptography can go wrong in a variety of different ways. One common cause is non-random secret keys. So if you've got a private key or secret key in a cryptographic algorithm, it's supposed to remain private or secret. And the best way to do that is to have a completely random value that you keep safe. However, sometimes in the interest of remembering that secret key, they're derived from poor sources of randomness or no source of randomness at all. If you take, say, the word password, hash it with SHA-256, well, you've got a 256-bit value that's just the right size for a secret key in some applications. And so the common way to try to create a memorable secret key. But if you can figure that out, so can other people. There's also commonly single-use values in cryptographic algorithms. One example is an initialization vector. And so this is just a public value, but it's supposed to be unique. And the reason for that is that when we encrypt two pieces of identical data, we don't want them to have identical ciphertexts. If so, we're telling anyone who looks at those ciphertexts that they're looking at the same piece of data. And so we throw a unique value in there to differentiate the two and result in a different encryption. And if we reuse that unique value for both, then all that hard work is wasted. The third common cause of cryptographic issues is a misuse of cryptographic algorithms. So there's few different types of cryptographic algorithms out there, and could be difficult to see which one's the right one for an application. I can't tell you the number of times someone's asked me, how do I decrypt this hash? It doesn't work like that. Or what's the secret key for a hash function? Again, doesn't work like that. And so using the wrong cryptographic algorithm can completely break security. Talk about that more in a moment as well. Another common issue is using insecure or broken algorithms. So if you've got an algorithm that, like DES, its key length is too short to be secure, it can be brute forced in minutes. And so if you're using an algorithm like that, or one that has known vulnerabilities, then the security of the crypto system is undermined and the data security is broken as well. And this is an ever-changing target. I mean, just a couple of weeks ago, one of the candidates for NIST's post-quantum cryptographic digital signature schemes was broken. They can break it on a laptop over a weekend. And this is one of the finalists in that scheme. And then finally, insecure secret keys. So say you've done everything right at key generation. You've got this nice random value created from a secure source of randomness, and you store it in a text file on your computer, or it accidentally ends up as part of a push to a GitHub repo. Well, if someone finds that, then it doesn't matter how strong the key is if you can find it in another way. So reason why we have these and many other ways that cryptography goes wrong is that cryptography is complicated. Even cryptographers get it wrong. Just mentioned the rainbow signature scheme being broken. When AES, the Advanced Encryption Standard, was created, NIST held a multi-year contest where a bunch of candidates were weeded out to get to the algorithm that we know today. And so a lot of these algorithms were created by well-respected, well-known cryptographers, but just a little flaw or a little bug in the protocol made everything fall apart. So some of them were broken in that 2 or 3 year period when they were being analyzed as a candidate for the next standardized form of encryption. And encryption algorithms that we know and trust today, like AES, are only trusted because no one's figured out how to break them yet. And so if cryptographers can get cryptography wrong, then most developers who aren't cryptographers, it's no wonder that we occasionally mess up and something goes wrong in one of the ways we see here or some other way. So unfortunately, data breaches that are caused by, or at least made possible by, cryptographic vulnerabilities are a regular occurrence. And part of the rationale behind saying this is data breaches are a daily occurrence at this point. We get major ones on a fairly regular basis. And by definition, if the data is encrypted and the attacker doesn't have the key, then it doesn't count as a breach. If you look at data protection regulations like HIPAA in the US, which protects healthcare data, they say that, well, if you're using a strong encryption algorithm, the keys weren't compromised, you don't have to bother reporting it. And so every time that we have a data breach containing sensitive information, we have at least the failure of not encrypting that data, and there's probably something else that went wrong along the way. And so let's look at a few example case studies of data encryption gone wrong in some way. One of these is what's called the blockchain bandit. So its name suggests this deals with blockchain technology, and in particular, the Ethereum blockchain. So at some point, people were using a tool to generate the private keys that are associated with their accounts on the blockchain. If you're not familiar, pretty much how account management and identity management works on the blockchain is that you generate your private key. From that can be derived a public key, so just like a digital signature scheme, and then the account address is derived from that public key. And so then you can generate digital signatures using a private key and a public key associated with a particular account. And so people were using a tool to generate these private keys that didn't do a very good job of it. And so it generated predictable private keys. Somebody figured this out and they started searching for them. And so by knowing what private keys this tool would generate, they could calculate the public keys and therefore the addresses. And so they monitored those addresses. And if someone put cryptocurrency into it, well, that cryptocurrency went right back out again. And researchers, once they discovered this, found that they were very, very fast at identifying and extracting value from these underprotected accounts. In some cases, it was minutes or even seconds between that initial deposit and the money being stolen by an attacker. And so that's an example of poor key generation in blockchain in this case. Another case of issue was a 2013 Adobe password breach. So this was a misuse of cryptographic algorithms issue, where instead of using a hash function to protect passwords, which is best practice, they used encryption. And so encryption with a single key meant that if those encrypted passwords were compromised and the key was compromised, then every password's compromised. In contrast with hash functions, each password and each hash would have to be individually guessed for them to be compromised. Because if you're hashing passwords correctly, you take that hash function, you pass in the combination of a salt, which is just another one of those single-use values, and the password, and calculate the result. And there's no way to go from that final hash output back to the original password. A third instance of a, in this case, famous cryptographic issue was Zerologon. So Zerologon was a case of rolling your own crypto or modifying cryptographic algorithms in a way that ended up making them insecure. So all of the bits and parts that were used for Zerologon were correct. They used a strong cryptographic algorithm. They used a strong block cipher mode of operation, which is used to define how different chunks of a block cipher encryption are performed. Because if you've got a block cipher like AES, you can only do 128 bits at a time, and you need some way to encrypt longer plain texts. And so they used a good algorithm, they used a good block cipher, but they made one small tweak, in which case they were encrypting only a portion of the ciphertext at a time. And so they'd perform an encryption, only keep one little bit of it, discard the rest, append to the end, rinse and repeat. And so end result was there were certain cases where if you had a plain text of all zeros, it would encrypt to a ciphertext of all zeros with probability 1/256. And so if that occurred, an attacker could bypass the authentication system for that WinLogon system. And that's what our Zerologon vulnerabilities found. And then finally, a fourth example here was a few years ago, Facebook discovered that internally, some of the applications written by Facebook developers were creating logs that were compromising user passwords, or at least storing them unencrypted on company machines. And so in this case, Facebook might have been storing passwords appropriately at other times. However, at some point, these applications needed access to passwords for some reason. And if something went wrong, or potentially even as part of their normal operations, they would write a log file to the server. And part of that log file would be a user's password. And so this went on for a while, nobody noticed it, and eventually somebody noticed it, and Facebook launched an internal investigation and eventually found that, yes, there's a certain number of passwords exposed on the servers, but there's no evidence that anyone misused them, even though they were the logs containing these plain text passwords were certainly accessed at various times as part of, say, normal employee duties. And so here's a case where maybe you're doing encryption the right way in one case, but there was some edge case or corner case that wasn't accounted for. And so sensitive data was left unencrypted. And these are just 4 examples of many, many, many potential that we could have talked about here, because as we mentioned, data breaches by definition are caused by some sort of failure of cryptography. Because if you've got encrypted data, then it doesn't count as a breach. So why are we having so much trouble with cryptography? One of the reasons why is cryptography is really complicated. I mean, take Zerologon, for example. They used all the right building blocks: strong cryptographic algorithm, strong block cipher, and all they did was, instead of encrypting for everything one chunk at a time on their blocks cipher, they used smaller pieces and only stored smaller pieces. That small change broke everything. And so that's just one example of the complexity of getting cryptography right and how fragile these algorithms can be. And so as a result, it can be difficult to do securely. So the simple answer of how do we stop cryptographic vulnerabilities and applications is making cryptography simpler. And so one contributor to the issues with cryptography in many applications is the complexity of libraries, cryptographic libraries. So there are many, many, many different cryptographic libraries out there, and all of them have different sets of supported algorithms. And so one of them might support AES, one of them might support Blowfish, RC4, RSA, et cetera, et cetera. And with different combinations, it can be difficult to choose which one is right. You have to decide, do I want to start out with, oh, I want this algorithm and I'll find a library that gives it to me? Or do I want to use this library and I'll pick whatever algorithms it gives me? Or the third, which one of these is easiest to use? And so when choosing between all of these, there's many considerations. There's the security. Is it good implementation of the algorithm? Is it protected against the various different potential threats to cryptography? And would I even know if it wasn't? There's performance. If this is an enterprise application, needs low latency, we need to make sure that cryptography doesn't eat up too much time, resources, et cetera. Regulatory compliance. Regulators sometimes specify that only certain algorithms are permitted. For example, AES is an official algorithm for the US government, and so compliance with those regulations might require the use of AES, and maybe not every library provides a compliant implementation. There's memory usage. Some algorithms eat up a ton of memory, others do not. Efficiency, future-proofness. Quantum computing will break certain types of public key or asymmetric cryptography. And so we need quantum or post-quantum or quantum resistant algorithms. Does a library provide those? And so these are just some of the considerations when choosing a cryptographic algorithm, a cryptographic library, and then that's just finding which implementation to use, not actually getting it to work. And so simple question is, why isn't there some way to just say, I want security, I need to encrypt something, why can't I just call an encrypt function and everything happens behind the scenes? And so making cryptography secure. So you don't want to write your own cryptographic implementation. You don't want to try to write AES or RSA or whatever on your own. There's a lot of different considerations that behind the scenes could break a cryptographic algorithm. Even if you implement the theory of a protocol perfectly, there are things like side channel attacks where the power consumption of the processor when performing certain operations can leak information about the secret key, the plain text, et cetera. And so writing your own implementation of a cryptographic algorithm is almost always a bad idea. And so using a good, trusted library implementation is better, but you have to choose the right implementation. And there's a lot of considerations that make it the right or the wrong one. It's not the right library if when you read the documentation, you still don't understand it. And that's assuming there's documentation at all. So you need a well-documented library where you could read through it and say, okay, if I do this, this, and this, I'm using the algorithm properly. And I've got security, integrity protection, whatever I'm looking for here. Second consideration is if you need to visit Stack Overflow to use it, it is not a good idea. And the reason for this is that there are definitely some good answers on Stack Overflow, absolutely. But there are also some where it's, well, I tried this and it worked. And while I tried this and it works in a lot of cases in programming, it's not a good idea in cryptography. So if you get back to that, well, I just needed a 256-bit value, I found one and it works, then something's possibly and even probably going to go wrong. And you might not even be able to tell whether or not that happened. And then a third is if you need to make judgment calls, unless you're a cryptographer or have a cryptography background and know, okay, this is the right block cipher mode of operation to use, or these are the pros and cons of this particular algorithm, et cetera, then having to make decisions about which cryptographic algorithm to use, which settings to use, et cetera, could be a problem. If you just choose the default for a block cipher mode of operation, and that's ECB mode, well, you're wasting your time essentially because it's not secure. And so you need to, when possible, find a library that makes the decisions for you, maybe even provides rationale for that. And so you know that you can just go through, call a well-documented series of functions or a single function, and everything just works. And then in addition to making sure you've got a good algorithm, make sure that those secret keys that you're using are stored securely. Can't tell you the number of companies at this point that have had secret keys that have just been accidentally exposed on GitHub, et cetera, and that breaks everything. And tests have found that if you expose a key on GitHub or similar repository, it could be found and used within minutes or hours, which is probably before someone will stumble across it in your organization and be like, that's not supposed to be here, and clean up afterward. And so just as a quick recap, why cryptography? Well, cryptography is vitally important in many applications for various different reasons: internal requirements for data security, regulatory compliance, et cetera. However, cryptography is really, really complicated and easy to get wrong. Just tweaking one small aspect of a protocol could break it entirely. And trying to design and write your own protocol is always a bad idea. Cryptography can go wrong in a variety of different ways. I talked about a few. You go take a look at OWASP. They have this huge list of CWEs that are linked to cryptographic failures, detailing many, many different ways in which cryptography can go wrong. Talked about a few case studies in where crypto went wrong, just failure to use strong private keys, using the wrong algorithm, tweaking the algorithm, and out of scope where data was stored in an unencrypted fashion. And so the main cause behind these cryptographic vulnerabilities we're seeing is cryptographic complexity. Cryptography is hard, nobody's made it easy, and so people mess up trying to make it work. And so when using cryptography, good idea to take the time to do the research and find an algorithm that in a library that works, is simple to understand, is secure, and actually meets your needs in a functional way, and that you can be confident that, okay, this is actually doing what I think it's doing and what I want it to do. Thank you. And then open up for any questions.
Awesome. Thank you so much, Howard. I do think we have one question in Slack.
Okay.
So Eli says, I tried this and it worked. Yes. But did you have an attacker using the world's biggest GPU to try and break it at the time?
Okay. Yeah. So if cryptography is implemented properly, then the world's biggest GPU shouldn't be a problem. So let's take an example where you've got a 256-bit secret key, which is applicable for many cryptographic algorithms. So 256-bit secret key has 2 to the 256 options. And for a level of context, you take the number of atoms in the known universe is only about 16 or so times, like on the order of 16 or so times larger than that number. And so if you're trying to just store that data, so on a modern hard drive, you will not be able to store every possible option for a 256-bit secret key because you need more than 16 atoms to store a bit of data. And so if you're doing it properly and cryptography is well implemented so that there's no weaknesses in the algorithm, the implementation's good, and the security comes down to the private key, then the world's biggest GPU isn't going to help you whatsoever. And so it's just getting to that assumption where the security is completely dependent on the private key is really where we need to get to, because that's where cryptography really provides its benefits.
Awesome. And a follow-up to that, what do you think could fix this problem? Better education, better libraries?
Yes, essentially. I mean, yeah, I think there have been numerous surveys over the years where developers have said, yes, I wish we got more training on various subjects. And cryptography definitely shows up on there because it's a specialist subject. I mean, cryptography, if you really, really, really want to be good at it, you're getting into very complex high-level math, et cetera. You need to understand attacks, and even people that know the subject don't know everything. So for example, I mentioned the AES contest before. So the one that got chosen, Urgendale, it was selected by the contest via NIST. And the NSA is like, hey, the S boxes that are used in this algorithm are good, but these ones are better. And we're not going to tell you why. And so several years later, differential cryptanalysis was discovered in the public sector outside of confidential government research. And they're like, oh, well, actually, the original S boxes were weak. They could have been broken in this way. And the NSA knew this years ago, and so they fixed it. But we didn't until now. And so if you want to get really, really good at crypto, it's a specialism. But there certainly is a level of knowledge where you can get to through better education and training. It's like, okay, I really understand what's the difference between a hash function and encryption algorithm, which one I should use here, why should an initialization vector only be used once, et cetera. And that training is great because it provides you with the ability to make rational decisions about what algorithms to use. And the other side of it is it's great that if those libraries that were available, it was clear, this is the right library for this use case, here's clear documentation. And so I'm not having to go on Stack Overflow and be like, how do I get this to work? I don't get it. And then have somebody explain how they got it to work, whether or not that's correct.